Hello everyone, this is Professor Ma, and this is the section on English trick controls. And what we will do, I will review the inverse functions, and in particular, we'll talk about the algebraic, the inverse identities. We will compose inverse, and then we will talk about what the graphs of a pair of inverse functions also look like. And then we apply that to inverse trig function. Particularly, we'll look at inverse cosine. So here we go. We start with functions. Okay, functions we say is to be one-to-one. If you put different input numbers in there to calculate the outputs, you will wind up with two different outputs. Okay, and a lot of time in mathematics, we show in these pictures, two u and v are two different things in the domain. Then your function f carries them to two different output fu, fv. Okay, and what's not a one-to-one? If you have some function that map two different things, take two different input, but wind up with the same output, then the function is not one-to-one. Okay, in particular, 2x plus 1 is 1-to-1. Okay, it's easy to see. If I put two different numbers in there and twice them, add on 1 to both of the answers, of course I wind up with different results, right? On the other hand, x squared is not 1-to-1 because I take 3, putting 3 squared, I get 9, and putting minus 3 squared, I get 9 also. So it's squaring is now 1-to-1. Okay. In particular, what it means is that if I know the output is 9, I wouldn't be able to pinpoint which one was the input. There's ambiguities. Okay. And sine of x is not 1-to-1. All the trigonometric functions are not 1-to-1. Okay, and in particular, why we want to talk about one-to-one? Because for one-to-one functions, we can define an inverse relationship. Because once I have a one-to-one functions, I know where it came from precisely. Then the reverse relations for any output you give me, I know the input. So that reverse relationship is a function. And that function we call f inverse. Remember, this f inverse exists precisely when original f was 1-to-1. Okay, this is very important. I have to start with 1-to-1 functions, then this f inverse exists. And that's why x squared inverse doesn't exist. Okay. But x squared, oh, by the way, if it does exist, then we have this very fundamental algebraic relation identity. That is, if I start out with an x and I follow around with this the trip or round trip with x goes from here into but f become f of x. The f inverse take it back to x. So when I compose f inverse, I get the identity function. I get x from x itself, and same way the other way around. Okay. So this is the important algebraic formula between a pair of inverse functions. When you compose them, you get the identity functions. X comes in, x goes in, x comes out. Okay, and we can solve for inverse. Okay, simple ones like these. And how? I mean, basically we're just saying solve for x. That's it. If I know, in other words, in this equation here, suppose I tell you I know what y is. I know the outcome of y, and what was the original input, x. So solve for the x, and in terms of y, and that's your inverse functions. Okay, and you can check. Oh, a lot of time we switch the variable when we write inverse, because this letter y is really I can use any variable I want to, since we kind of in general talks about functions as functions of the variable x as the dummy variable. So we therefore talk about f inverse of x. Okay. Strictly f inverse is a function of y, but this we treated the f inverse as a function of x. Okay. And now let's come to the functions where it's not one-to-one, like the x squared. Okay, we can make a one-to-one if we restrict the domain. The problem with the x squared is not one-to-one, I get plus and minus going to the same thing, is the domain is too big. I can restrict it to just a positive number. Okay, and I can talk about inverse, okay? So it's not one-to-one because it's too big. But so if I restrict my function, say, oh, now I only look at the portion where x is positive or 0. Okay. And now when I take the square root, okay, when I take when I give you the number 9, that I know exactly what x is. X is going to be square root of 9. That exist because I know where it came from, because the domain is restricted. Okay. So, for example, this is the function g of x equals x squared for x bigger than equal to 0. Okay. And if I tell you the number 9, and if I say this is 9 over here, now I know exactly where 9 came from. Okay, 9 came from x equal to 3. So its inverse is square root of 9. Okay, and it has an inverse. So, second things, so the inverse functions really depends on the domain. If a function is not one-to-one, I can restrict the function to a portion of the original, which is one-to-one, and talk about its inverse just within that portion. And this is what we're going to do with cosine. Okay. And the second thing about inverse function, notice the graph. Okay. Oh, by the way, you can verify, okay, if I compose f inverse of x with square root of x and x, and like it's square root of x squared, and that's what x, right? That's the identity we were talking about. So this is a simple verification. The second thing about the inverse pair of functions, the graphs. If f of a becomes b, and that with the points a, b on the graph of y equal to f of x, its inverse function will take the b back to a, right? So f inverse of b therefore go to a, and that is b of, if you feeding b, you will get a. That's a point on the inverse. Okay, so the implication on the picture is for any AB on the original pictures, you will get the points BA on the inverse pictures. If you plot through all of these points on f of x, you get these reflections across the identity for the graphs of the inverse function. Okay. So the graph f inverse are symmetric diagonally. Okay. Now let's come to trigonometry function. Cosine is not one-to-one. Cosine 0, 2 pi. The many angles. I wind up with the same output 1. So I need to restrict cosine to only the portions of the domains. So I can talk about, so that is one-to-one. So I can talk about its inverse, and this is where we do it. Okay, we're going to restrict it from 0 to pi. Why? Because if I view this function from 0 to pi, its range output is from -1 to 1. And then this function is 1 to 1 with this specific domain and range. Okay. And its inverse exists. And we call the inverse cosine inverse of some number A, because A was the original output. If this is y, that's the cosine inverse of y. The cosine inverse x takes inputs from here, or any value that shows up in -1 to 1. And it mapped back to the original angle we came from. Pictures. And we can plot it. We can kind of notice the original formula cosine takes 0 pi to -1 to 1. So the cosine inverse will take -1 to 1 to 0 to 2 pi. It's the other way around. Okay. So we'll graph it shortly, but let's figure out some of the answer which we can actually know what the inverse, like what's inverse of 1/2 of cosine. You think about for a second. Oh, pi over 3. Right, 6 degrees. You know. You think of whichever way you want to think of it. -1/2. Well, 2/3. Okay. 5/3. 5/2. Okay. Notice the third one. It's a little bit. You have to be a little careful because cosine inverse, if I just give you the question, say what's cosine inverse of 5 pi over 3, it is not 5 pi over 3 because cosine of 5 pi over 3 is 1/2 and cosine inverse of 1/2 take it back to pi over 3, so it's not pi. Okay, notice that because of this restriction. And here's the graph. Okay, remember, we can reflect across the diagonally. And here's the graph of y equal to cosine inverse. Okay, if I graph on the same x, y axis, and you have these symmetrical, diagonal symmetric graphs. Okay, and so this is cosine inverse function, and this is its graph. And notice, cosine inverse graph is one of these graphs which is just cuts out. Just has it's in your box. It's from one end to the box. The other, that's it. It's a short segment of a function. Okay. And there are other ways to visualize what cosine inverse in terms of what the output cosine inverse is, the angle is supposed to be. Okay, so cosine is the x-axis. If I put on the unit circle. Okay. So given points A, B, okay, and cosine, suppose A is cosine, x-axis is cosine theta, right? So cosine inverse of the number A, if you give me an A, you locate it on the x-axis where it is. If A is positive, it's on the right-hand side. If A is negative, it's on the left-hand side, right? But so right now it's on the positive side. Then, and there's a point on this unit circle that corresponds to on the 0 to pi correspond to the x coordinate to be A, and that the angle is cosine inverse of A. And there's another things we use to represent the cosine inverse of angle, which is a reference angle. Okay. Cosine inverse of A is an angle, right? A. Then we use the SOHCAHTOA definitions of an angle. Okay, so this is the angle triangle represent the angle whose cosine. So its cosine is A over 1. Okay, therefore, But for this, cosine theta is A over 1. This is, you know, and the SOHCAHTOA, this is the car. Okay, adjacent over hypotenuse. Hypotenuse 1. So this triangle, we call this triangle the reference triangle or the picture triangle for cosine inverse. Okay, and what is it good for? Well, because if I once have, basically it says cosine inverse of a number, basically it nailed down what the angle has to be. Pretty much, you have two choices. This is one representation of a triangle of that angle. And we basically know what the third side is. We know precisely what the third side is. And from this picture, complete angle pictures of theta, we can extract other values of trig values. So for example, what's cosine inverse of -3/5 of sine? Okay, I can view as this triangle here, and then the third side must be 4. So this therefore must be the cosine. This must be the angle theta. Okay, this the inverse trig is always an angle. It's the angle theta, and then sine of theta. I can just read it off. That's what sine of theta. Sine of theta was opposite over the 4/5. And I can use this to do abstract angles of formulas. Suppose what's cotangent cosine inverse of 2. So again, if I represent this by an angle theta, okay, then cosine of theta must be 2a over 1. Then I can draw this triangle adjacent over hypotenuse. Okay, again, you just put the numerators for the adjacent, 1 for the hypotenuse. And that would tell you the third sides has to be by Pythagorean theory. And this is the reference angle to that. That's the reference angle for theta. Now I want to extract cotangent of theta. I just then extract a cotangent of theta by reading out that reference triangle. We will use this trick in next time when we talk about derivatives of these angles. Okay. And similarly, we define sine, except we restrict the sine to be from -π/2 to π/2, the domain. Okay. To make, remember, we have to make the sine function 1-to-1. And where do we extract it? We extract it from -π/2, and here's the graph of it. Okay. And here, this is sine, and in these segments, it's 1-to-1. So I can take the inverse functions, and its functions, the domain will be now -1-to-1. Range is -π/2 to π/2. Is this rectangle flipped over? Okay, it's reflection across y equal to x. And so y equal to sine of x is the red line. It's reflection of the blue line, sine of x. And it has a function, reflection is a function because sine of x is 1-to-1 within -π/2 to π/2. Okay. So it has these pictures associating with the semicircle of the angles that I'm extracting from -π/2 to π/2. Okay, yeah, -π/2. So theta will be somewhere between there, and this is the reference triangle for sine inverse of a number. Okay, and similarly with tangent inverse, I will read that for you to read. And we'll leave that for you to read. And this is tangent. And where do we extract tangents is 1-to-1. We just take one period of it, -π to π, -π/2 to π/2. And then its inverse, when you reflect across diagonal, it's this entire strip gets flipped horizontally. It's like take a length of the strips, and now I lay horizontally. Okay, become that. So that's tangent inverse. Tangent inverse is one peculiar things about tangent inverse. Its domain is entire real line, but it's trapped between minus pi over 2 to pi over 2. So within the strips. Okay, so these functions it has that peculiar properties for tangent inverse. And I include then the other trig inverse, which it's in the book, and you can read about their definition. They define similarly, and they have the same pictures in terms of reference angles, reference triangles, and these are the perspective, the graph of inverse functions of the other three trig functions. Okay, that's it. Okay, bye-bye. Until next time.